Okay, what we're going to have a look now is the formula we use when we're dealing with vector instead of scalar. So scalar is speed, distance and time. Vector is velocity, displacement and time. Now it's similar but different, and it's quite important that we see the difference in it. For example, average velocity is v. That makes a fair bit of sense. Displacement is s and time is t. Now you might be wondering to yourself, why has Mr. Matheson changed the letters? It's mainly because when we look to more complicated equations of motion, we need these letters. Average velocity is displacement divided by time. Total displacement is velocity multiplied by time. And time is displacement divided by velocity. So you could just write that as v equals s over t. S equals v times t, and t equals s over v. What are the units for velocity, displacement and time? Well, this is good because they're just the same. Velocity equals s, so that's meters per second. No, it's not. Start again. Velocity equals v, which is meters per second. Time is still seconds. And displacement which is s in this case, is meters. Didn't do that very neatly, did I? That's better. So time in seconds, velocity in meters per second, and displacement in meters. Normally, also when we're giving a direction or a speed, when we're giving a displacement or a speed, giving the direction is difficult. Sometimes it could just be positive or negative. Say positive if the speed isn't going away from you, negative if it's coming towards you, or we use a simple north, south, east, west. Try not to make it too complicated. An example question, okay? So you might have watched this in the Olympics over the summer. The cyclists cycling round and round in a circle really quickly. We can all pretend we weren't watching it, just waiting to see if someone fell off, because it's always entertaining. The speeds they get up to is incredible, which means they fall in an incredible way. The velodrome is a curved cycle track that cyclists race round for numerous laps. Total distance around the track is 400 meters. So there's our track. And for the purpose of the question, assuming there's a perfect circle. So what we're saying is the perimeter is 400 meters. The time for a standard Olympic standard cyclist to do one lap is 18 seconds. Sounds nuts. So what distance does a cyclist travel after one lap? Well, that would be our 400 meters. So the average speed equals distance divided by time. 400 divided by our 18 seconds. It's going to be quite impressive, I reckon. Divided by 18, so that's 22.2 meters per second. So this is where it gets confusing. What is the displacement of the cyclist from the starting point after half a lap? Think about it. It's a circular lap. That's the start point. Half a lap, he's here. So the displacement would be the diameter. And you could work that out using 2 pi r, I guess, pi d. So the perimeter equals pi d. I'm not going to do that though. What's the displacement of the cyclist after one lap? Well, after one lap, he or she has gone round and ended up back where they started. So it's 0 meters. So this means that our Olympic cyclist, who has given all that they've got, after one lap, we would be within our rights to say their average velocity is 0 meters per second. Simple as that. Now, I'm going to leave it at that. And what I'm going to do is post some calculations questions up. I'd like you to complete up to page 10 in your booklet. And then I'll put some calculations questions up for you.